Welcome back to the Deep Dive. Our mission here, as always, is to take some of the most challenging and dense research out there and really distill it into immediate, actionable knowledge for you.
And today, we are standing right at a fascinating junction. It's where fundamental physics slams right into the cutting edge of machine learning.
We're going to find out how artificial intelligence is being used to fix a really critical physical roadblock. A roadblock that limits access to some of the most exotic, powerful light sources on the planet.
It's a genuinely exciting application.
Okay, let's unpack this. We're deep diving into the automation of something called high harmonic generation, or HHG.
Right.
Now, if you've been following advanced laser science, you know the holy grail is shrinking massive infrastructure down to a tabletop size.
And that's exactly what this is. We're talking about generating powerful, coherent, ultra-short radiation pulses, the kind of light you find in the extreme ultraviolet, the EUV, and soft X-ray range.
And historically, this kind of radiation was, it was exclusively the domain of enormous multi-billion-dollar facilities.
Yeah.
Things like synchrotrons.
Huge, city block-sized machines.
Exactly. So the fact that researchers can now do this in a university lab,
Yeah.
that's the massive hook here.
It really is. It's a technological leap with some pretty profound scientific implications. You see, you need this specific kind of light because of its properties.
It's not just any light.
Not at all. It's coherent, which means the waves are all synchronized, and critically, it's ultra-fast. We are talking femtoseconds, even down to attoseconds.
So why do we care? Why go to all this trouble?
Well, these pulses are absolutely vital for things like photoemission spectroscopy. That's what lets condensed matter physicists probe the electronic structure of materials with incredible precision.
Okay.
They're also used in pump probe spectroscopy to look at fleeting high-energy density plasmas. And because the generation process itself naturally produces the shortest pulses known to man, they are foundational to the entire field of attosecond science.
Which is, that's just mind-boggling.
Yeah.
You're giving us the ability to actually film electron motion.
You're filming the universe at its fundamental speed limit. But, and this is a huge but, that immense power comes with an equally massive operational challenge.
Right. To drive this HHG process, you need an incredibly intense high-power laser pulse. And squeezing all that energy into a tiny focal spot requires pristine, perfect optics.
And the moment you introduce complex optics lenses, mirrors, vacuum windows, you introduce errors.
Or what physicists call optical aberrations.
Exactly. And the problem isn't just aesthetic, It's not about a pretty picture. It's fundamental to the efficiency of the whole system.
How so?
Well, these aberrations, they degrade the beam quality. They spread out the focal spot, which significantly reduces the peak intensity that you deliver to the gas cell.
And that's where the magic happens.
That's where it all happens. And because harmonic generation scales non-linearly, we're talking by the 10th power or even higher with that driving field intensity.
Oh.
Even a small reduction in the focus quality causes the XUV output to just fall off a cliff. The experiment basically fails to deliver anything near its maximum potential.
So you have this complex system that's constantly striving for perfect focus, and it's constantly fighting against environmental and physical imperfections.
Right. And the traditional way of fixing this manual alignment is just so time-consuming. It's tedious, and frankly, it's often not good enough for these systems that demand absolute perfection.
So our mission in this deep dive is to explore the automated solution, how machine learning provides an intelligent shortcut.
We're looking at two really distinct approaches. First, Bayesian optimization, or BO, and second, a convolutional neural network, a CNN.
And how they command this key piece of hardware, the spatial light modulator, or SLM, to actively correct the distorted wavefront in real time and maximize that harmonic yield.
Before we jump into the AI solutions, we absolutely have to establish the analytical foundation. Why is the HHG process so incredibly sensitive to the beam quality?
It all comes back to the physics, doesn't it?
It all comes back to the intense laser-matter interaction.
Okay, so let's start at the source. Give us the technical definition of high harmonic generation.
So HHG is what we call a highly nonlinear optical process. It involves an incredibly intense laser field interacting with the material, and in this case, it's typically a noble gas like neon or krypton.
And when you say intense?
We're talking intensities upwards of 10 to the 14 watts per square centimeter. When you hit that threshold, the light that comes out isn't just the original frequency or its simple multiples.
Right.
Instead, the interaction generates these discrete odd integer multiples of the fundamental frequency. We call them harmonics, specifically those above the fifth harmonic.
That's the output. But the mechanism underneath it all is it's really unique. You mentioned the classical understanding is framed by this three-step model. Can you walk us through what's happening to the electron?
I can. The three-step model gives us a semi-classical but a surprisingly accurate picture of this ultra-fast interaction.
Okay, step one.
Step one is tunneling ionization. When the laser's electric field is at its absolute peak strength, it's so intense that it literally distorts the Coulomb potential barrier holding the electron to its nucleus.
It's bending the rules of the atom.
It's bending them to the breaking point. This distortion lowers and thins the barrier so much that the valence electron doesn't just classically escape. It quantum mechanically tunnels right out into the open.
And it just appears outside the atom.
It's born essentially stationary right outside that potential.
Wow. So now this electron is just floating in an extremely powerful oscillating electric field. What happens next?
That brings us to step two, acceleration. Once it's free, the electron is immediately accelerated away from its parent ion by that driving laser field.
Okay.
Now, since the laser field is oscillating, the electron's direction and its kinetic energy are totally governed by the exact phase in the field at the moment it was born.
And that timing is critical.
It's everything. For the electron to ever return to the ion, which is crucial for the next step, it has to be born roughly within a quarter of the laser cycle before the field reverses. As it travels away, it gains a huge amount of kinetic energy.
And then the field flips.
The field flips. Step three, recombination and emission. After about half a laser period, the electric field reverses direction, and it accelerates the electron back towards the parent atom.
Like a boomerang.
A very, very high-energy boomerang. When that electron slams back into the ion, it recombines, and it releases all of that accumulated kinetic energy instantaneously as a single high-energy photon.
And that's our harmonic.
That is the high harmonic photon. Its energy is basically the sum of the atom's ionization potential plus the maximum kinetic energy the electron gained during its little trip.
And that timing, the fact that recombination only happens over this tiny fraction of the laser cycle, that's the key to the famous attosecond pulse duration, isn't it?
Absolutely. Because that high-energy emission only happens during that fleeting moment of recombination, the resulting XUV pulse is dramatically shorter than the initial 30 femtosecond driving pulse.
It's temporal confinement.
It's a natural byproduct of the nonlinear physics, and it's what enables all those attosecond scale applications. But the whole process hinges on achieving the highest possible field strength, the highest peak intensity at the focus.
Which brings us right back to the problem of distortion. If the beam isn't perfect, the intensity drops and the whole mechanism it doesn't launch optimally.
Right.
So we need a way to quantify and describe this messiness so we can correct it.
And that is the role of Zernike polynomials. If you think of the wavefront of the laser beam as a kind of landscape, Zernike polynomials provide the standardized vocabulary to describe every hill, every valley, and every slope on that landscape.
They're the mathematical standard for this.
They are. They're standard in adaptive optics because they form a complete orthogonal basis set over a unit circle, which maps perfectly to the circular aperture of our beam path.
Now, you used a word there, orthogonal. Why is that so critical here?
Orthogonality is what makes them so incredibly useful for correction systems. In simple terms, it means that if you adjust the coefficient for one type of aberration, let's say defocus, you are guaranteed not to accidentally introduce or change the amount of astigmatism or coma in your system.
So each knob is independent.
Each knob is independent. It decouples the aberrations, which makes the whole optimization problem much, much cleaner than if we were trying to use a standard Taylor series expansion or something.
So the wavefront distortion is just a weighted sum of these polynomials.
Exactly. Each weight, we call it NL, is the coefficient we need to find, and it represents the strength of that specific aberration.
So a lower order polynomial might be a simple defocus. If that coefficient is high, your focus is just bad.
Precisely. The low orders represent the gross distortions that are most easily introduced by simple misalignment. Things like defocus, astigmatism, and tip tilt.
And the higher orders?
Those describe more complex, subtle distortions like coma or spherical aberration, the kind of thing you get from thermal effects or, poorly manufactured optics.
So once the machine learning system figures out those coefficients that describe the distortion, That tells us exactly what we need to apply to the correction device.
Which is the spatial light modulator, or SLM. It's essentially a programmable mirror array. We're talking a grid of maybe 1,000 by 1,000 pixels.
Like a tiny high-tech screen for light.
That's a great way to put it. By applying specific voltages to these pixels, we can control the phase delay across the beam's profile. The goal of the entire optimization process is to find the perfect set of Zernike coefficients for the SLM to apply the negative of the measured aberration, the phase conjugate.
So it adds the opposite distortion to cancel out the original one.
Exactly. When the distorted beam hits the SLM adds that negative phase map, and it effectively flattens the wavefront back to perfection. A flat wavefront gives you the best focus quality, which maximizes peak intensity, and that maximizes the HHG efficiency.
And if we were assessing the final beam quality, we'd ideally be looking at something called the Strail ratio, right? Since we mentioned it for our listener, how do we define that in the context of what we're trying to achieve here?
The Strail ratio is really the gold standard for optical quality. It's defined as the ratio of the peak intensity of your aberrated focal spot to the theoretical maximum peak intensity you could get from a perfect unaberrated system.
So a perfect beam is 1.0.
A perfect beam has a Strail ratio of 1.0. And if we had a sensor that could directly measure this in real time, the goal of the machine learning would simply be to maximize that Strail ratio. But direct Strail measurement in these high-power XUV systems is often impractical, which is why optimizing the total harmonic signal becomes the proxy.
Okay, so we've established the theoretical need for correction. Now, let's ground this in the real world of the laboratory.
Yeah.
What does the full apparatus look like, and what are the specific constraints the machine learning has to work within?
Well, the apparatus starts with the driving laser, which is a high-power titanium sapphire pulsed laser system. The source material gives us the key parameters, an 800 nanometer wavelength, so that's near infrared,
Right.
a pulse duration of about 30 femtoseconds, and a repetition rate of 1 kilohertz. So these are extremely short, frequent, and very high-intensity pulses.
And all that energy has to be guided and focused with incredible precision.
Precisely. The beam travels through a whole series of optical elements and is eventually directed into a vacuum chamber.
And it has to be a vacuum.
Has to be. Soft X-rays are strongly absorbed by air. So inside that vacuum, the beam is focused onto a tiny gas cell, which contains krypton at around 100 millibar of pressure. That small volume is the heart of the whole HHG process.
And then you measure the output.
Critically, the success of the experiment is measured downstream. They use a specialized Great Eyes UV camera, an ALXI model, at the end of the vacuum path. This camera is sensitive to those high-energy XUV photons and provides the raw data, the harmonic signal that our algorithms are trying to maximize.
Let's talk a bit more about that SLM integration. It's not just a mirror. It's a dynamic, programmable element. What are the specific challenges of putting one of those into a high-power system like this?
The main challenge is handling the diffractive nature of the SLM. Since the SLM applies phase by modulating its surface, it inevitably creates multiple diffracted orders, kind of like a diffraction grating.
So it splits the beam.
It splits the light into a zeroth order, which is the undiffracted light that carries no correction, and then the first, second, and higher orders.
And you only want one of those.
For the experiment to work, only the first order diffracted beam, the one carrying that meticulously calculated Zernike phase map, is allowed to continue into the vacuum chamber and to the focus.
What happens to the rest?
All the other orders, including that massive zeroth order, have to be physically blocked by a precisely placed iris or aperture just upstream of the focus. This filtering process adds another whole layer of complexity to the alignment. If the SLM is misaligned, the first order moves, the intensity drops, and the system fails.
This complexity, this delicacy, and just the sheer number of variables, it all just screams for automation. What did the manual optimization process look like, and why did it become so unsustainable?
The initial work in the lab, as detailed in the source, involves some really painstaking manual optimization. For example, a researcher might focus on optimizing just one Zernike mode, say oblique astigmatism.
Okay.
They would literally sweep the coefficient manually, stepping from 0.03 to 0.24 in small fixed increments, and watch the total HHG signal on a screen. This works, for one dimension. They can find the peak.
But imagine you're dealing with a system that drifts because of thermal effects, and you need to simultaneously optimize the 5 most dominant lower-order modes. focus, vertical astigmatism, oblique astigmatism, vertical coma, and horizontal coma.
That's 5 variables acting on the wavefront all at once. If you try the brute force, one-at-a-time approach, the time penalty is just staggering.
It's mathematically prohibitive.
It is. Even if a researcher only tested 10 equally spaced values for each of those 5 dimensions, you're looking at 10 to the power of 5, or 100,000 unique measurements.
What's 100,000?
And if each measurement takes just a second or two to stabilize and acquire, which is optimistic, you've just consumed days of valuable, high-power laser time for one alignment, an alignment which is going to drift away quickly anyway.
So the core objective here isn't just optimization, it's smart optimization. It's something that can overcome the curse of dimensionality and the time constraints of a high-power lab environment.
Exactly. The mission became, let's develop machine learning methods that can quickly and intelligently navigate this high-dimensional Zernike space to find the optimal phase map for the SLM, ensuring maximum HG efficiency without needing weeks of dedicated alignment time from a human expert.
Okay, so the first machine learning strategy they employed was Bayesian optimization, or a BO. This is often seen as a smarter, more structured approach compared to just, brute force grid searches.
That's right.
How does BO fundamentally differ, and why was it chosen as the first shot at automation?
Well, BO is really ideal for optimizing what we call expensive black box functions. These are functions where just getting a single data point is costly, like waiting for the HHG system to stabilize and measure the output.
And unlike a random search.
Right. Unlike a random or a grid search, BO maintains a probabilistic model of the objective function, and it typically uses something called Gaussian processes for this.
So what does that mean in practice?
Think of it this way. BO looks at all the points it has already tested where it knows the exact HHG output, and it fits a curve, the Gaussian process, to those results. This model gives it 2 critical things: an estimate of the output at any untested point, and just as important, the uncertainty of that estimate.
So that estimate is the key to efficiency. It doesn't waste time looking in areas that are likely to be bad.
Correct. It uses what's called an acquisition function, a kind of decision rule, to select the next point it should sample. This function balances 2 strategies. On one hand, you have exploitation, which is testing areas where the model predicts the output will be high.
And the other?
Exploration. That's testing areas where the uncertainty is high, even if the current prediction is mediocre, because there might be a surprise global optimum hiding in there. This systematic, intelligent search allows BO to converge on an optimal solution much, much faster than traditional methods.
And they implemented this using the BaseOp function in MATLAB. Which 5 Zernike modes were they targeting for optimization in this initial BO step?
As we mentioned, they focus on those dominant low-order aberrations: focus, vertical astigmatism, oblique astigmatism, vertical coma, and horizontal coma. These modes were chosen because they're the primary drivers of focal spot degradation in a typical setup.
And their approach wasn't just to throw all 5 modes into the optimizer at once, right? They had a more methodical strategy.
A very methodical, multi-stage strategy. Step 1 was individual mode optimization. They ran 30 iterations to maximize the peak intensity for each of the 5 modes individually.
So they'd hold 4 constant and just vary 1?
Exactly. The other 4 modes were fixed at 0 or some baseline value, and they'd only vary 1, searching within a predefined range, for instance, running focus from -0.6 to -0.2.
This essentially gives them a really robust starting point. It confirms the optimal setting for each aberration when it's acting alone.
That's exactly right. And that leads directly to step 2, refinement. Based on the optimal values they found for each mode in isolation, they could then significantly narrow the search ranges for the final step.
So if the best focus was found at -0.4,
they might set the final search range for the joint optimization to something like -0.5, negative or 0.3, focusing all the computational power where the solution is most likely to be.
and then the final step.
Step 3 was the joint optimization. They ran another 30 iterations, but this time they were varying all 5 Zernike amplitudes simultaneously within those newly refined search ranges. This is the stage where the complex interactions between the aberration modes, the coupling, are finally captured and optimized.
This multi-stage process seems highly practical for a physical experiment where you want to minimize the number of iterations while still making sure you converge. What were the successes?
The main success was proving viability. BO provided a systematic, a rigorous way to explore the parameter space, and it confirmed that automated optimization was absolutely feasible. By starting with individual optimization, they got a significant efficiency gain in the later joint search. It established a strong interpretable baseline for what the optimal coefficients should look like.
Despite its success in finding a peak, BO has these inherent structural limitations that eventually force them to look for something else. What were those critical trade-offs?
Well, the primary limitation is its fundamental sequential nature. Even with that joint optimization step, BO still relies on iterative sampling. You're always waiting for the previous measurement to inform the next guess. And while it's faster than a grid search, it's still relatively slow.
And there was a more fundamental physics problem with that sequential approach.
Yes. As we discussed earlier, aberrations are coupled in a real optical system. Optimizing focus first, then astigmatism, might lock the system into what we call a local optimum. The best focus setting might actually rely on the presence of a specific amount of coma, for example.
So by doing them one by one, they risked missing the true global optimum.
An optimum that might require highly correlated changes across all 5 modes at the same time.
And the second major limitation was its objective function. It was only maximizing the peak pixel intensity.
Correct. BO was designed for a single objective, maximum brightness. It completely ignores beam quality. You can have a very bright but highly asymmetric or messy focal spot, a low Strehl ratio that still registers a high peak count.
And for a sensitive nonlinear process like HEFE, a high-quality Gaussian-like beam is far more stable and efficient than a sharp but erratic one.
Exactly. The BO system just wasn't sophisticated enough to monitor beam shape or the overall quality metrics you need for long-term experimental stability. This lack of finesse in the optimization objective is what pushed them toward a method that could actually see the image.
So before we get to the CNN, let's quickly acknowledge the difficulty of working with the XUV output itself. The researchers adapted their scripts to use that specialized Great Eyes XUV camera, which gave them better resolution on the final harmonic product. And this led to a fascinating analytical attempt.
It did, yes. They needed a way to verify which harmonics they were actually generating.
Sure.
And the setup they used inherently produces an interference pattern on the XUV camera chip.
Why is that?
It's because the high-power laser beam is split to create 2 spatially separated HHG sources.
So the resulting image isn't a clean spot, but a series of fringes, like in a double-slit experiment.
Exactly. The fringe spacing, let's call it $, is dependent on the wavelength of that specific harmonic, the distance to the detector, which was about 3 meters, and the source separation, which was about 75 micrometers. So if you can measure the fringe spacing, you can figure out the wavelength.
But measuring that spacing directly on a raw XUV image, which you said is complex and noisy, that sounds like a nightmare.
It is, especially in the XUV range. These photons are high energy, and the detection system just inherently introduces noise. To get around this, they applied a 2-dimensional spatial Fourier transform to the images.
So you go from real space to frequency space.
Right. The Fourier transform maps those periodic fringes, which are spatial features, into distinct peaks in the frequency domain. These are the spatial frequencies, FIVR.
So measuring the location of a peak in Fourier space is the same as measuring the fringe spacing in real space.
Precisely. They would extract the intensity profile along a line in Fourier space, identify the peak pixel indices, and then convert these back to spatial frequencies, fringe spacings, and ultimately wavelengths.
And they analyzed 11 measured peaks across several images to try and identify the genuine harmonics. The expectation was that the wavelengths would follow that simple harmonic relationship, lambda-dan.
That was the hope.
And what did they find?
The results were highly inconsistent. Calculated wavelengths and fringe spacings just did not conform to the expected integer harmonic relationships at all. The analysis failed to reliably identify which peaks corresponded to which specific genuine odd integer harmonic. It really confirmed how difficult spectroscopic analysis is with this geometry.
This just highlights the immense difficulty of XUV measurement. What were the identified sources of this analytical failure?
Well, there were environmental factors and technical limitations. First, physical misalignment of the system was a major suspect. The fringe spacing relies entirely on the precise separation of those 2 HHG sources.
That tiny 75 micrometer distance.
Yes. Any drift or variation in that tiny separation due to thermal effects or vibration immediately invalidates the entire fringe spacing calculation.
And the noise?
Second, the high noise sensitivity of the Fourier transform itself. XUV detectors are noisy, and that noise creates spurious non-harmonic peaks in the frequency domain. which makes identifying the genuine harmonics
Then
ambiguous.
there was the camera itself.
Right, the limited resolution of the camera, the pixel pitch was 13.5 micrometers, and that fundamentally limited the precision with which they could locate the peaks in Fourier space. That error then propagated into a significant uncertainty in the final calculated wavelength.
So the analytical method was sound in theory, but the messy reality of the high-power XUV experiment, the noise, the misalignment, the limited resolution, it rendered the results unreliable for any kind of spectroscopic purpose.
It did.
And this failure of output analysis actually reinforces the need to focus entirely on controlling the input.
Exactly. If we can't reliably diagnose the output, we have to ensure the input laser beam is absolutely perfect, eliminating the aberrations that cause instability in the first place. This realization provided a really strong impetus to move away from sequential optimization like BO to a method capable of instantaneous image-based correction, the CNN.
And this is where the deep learning really begins. We've established that BO was too slow and only optimized for peak intensity. The CNN, in contrast, is designed to extract spatial features and provide an instant diagnosis.
That's right.
The motivation, fundamentally, was moving beyond a single metric to true pattern recognition.
Absolutely. The CNN's strength is in spatial pattern recognition. Aberrations manifest as unique shapes in the focal spot. Astigmatism looks like a cross, coma looks like a comet tail. A CNN can learn to recognize these shapes and relate them directly to the underlying Zernike coefficients.
And crucially, they bypassed the traditional methods of phase retrieval.
They did. They didn't use a separate sensor to reconstruct the phase, which is complex and expensive. Instead, the CNN learned the direct nonlinear mapping. Focal spot image goes in, Zernike coefficients come out.
So the ultimate goal is that once the network looks at the distorted image and predicts the coefficients, the SLM instantly applies the negative of those coefficients for correction.
That's the dream. Instant correction.
Now, for the CNN to learn, it needs fuel. It needs a large, high-quality data set. What specific aberrations did they restrict the training to, and why?
They focused on predicting coefficients for Zernike orders 4, 5, and 6. So that's focus, vertical astigmatism, and oblique astigmatism.
They excluded the first three orders.
They did. Orders 1, 2, and 3, piston, tip, and tilt, were excluded because they don't represent intrinsic wavefront curvature aberrations. Tip and tilt are usually just fixed mechanically, and piston is a constant phase offset that doesn't affect your focal quality.
Okay, so how did they build the data set?
They use the SLM to systematically introduce controlled, random aberrations corresponding to those three orders. For each unique set of coefficients they applied, they took an image of the resulting focal spot using a Thorlabs camera. This generated 506 unique image and coefficient pairs.
506 images. That number really stands out because the source comparison notes that other adaptive optics work uses something like 18,000 images.
Yes.
Given that massive disparity, wasn't there an immediate fear that this was just way too small for a meaningful deep learning model?
Absolutely. This is the primary bottleneck and a major limiting factor in the entire study. 506 images, by deep learning standards, is tiny. It drastically increases the risk of overfitting.
Where the model just memorizes the training data.
Exactly. The model learns the idiosyncrasies of the training set, but then fails to generalize to any new aberration it hasn't specifically seen before. The viability of the final result hinges entirely on whether the CNN can overcome this data deficit.
That makes the pre-processing steps absolutely essential for standardizing the input. How do they prepare those 506 images for the network?
Consistency is paramount for CNNs. Since the beam might move slightly or the spot size might vary, they needed a standard input size. The script performed several key steps.
Okay.
First was image normalization and thresholding. This converts the raw image data into a clean binary representation, separating the spot from the background noise. Second, they found the contours within that binary image and identified the single largest contour, which represents the focal spot itself.
And then they just cropped around that.
Finally, yes, they cropped the image to a standard bounding rectangle centered on that spot. This ensures the CNN receives a consistent, focused representation of the aberration, and it ignores any external noise or translational movement.
So let's delve into the actual structure of the convolutional neural network. This is a regression task. It's predicting continuous coefficients, so the architecture has to be geared toward feature extraction and numerical output.
Right. The architecture was a pretty straightforward sequential design, and it was optimized for feature extraction from images. It used three primary convolutional blocks.
What were they?
The first convolutional layer had 32 filters, the second and third had 64 filters, and they all used small 3 by 3 kernels. These kernels are highly effective at extracting local spatial features, things like edges, corners, and curvature, which are the building blocks of aberration recognition.
And what was the purpose of the pooling layers that were interspersed between those convolution layers?
They used 2 by 2 max pooling layers after each convolution step, and max pooling serves two critical purposes. First, it drastically reduces the spatial dimensionality of the image data,
Okay.
which makes the network computationally feasible.
And second,
Second, it provides something called translation invariance. This means if the focal spot moves slightly within the input crop, the CNN can still recognize the core features of the aberration. It makes the model more robust.
and after the convolutional blocks.
The output was flattened into a vector and then fed into a dense layer of 64 neurons using real U activation. Real U is computationally efficient, and it introduces the necessary nonlinearity to map these complex aberration shapes to a simple coefficient output.
And finally, the output layer itself.
The output layer was minimal, just 3 neurons, one for each of the Zernike coefficients they were predicting. And critically, these output neurons use linear activation. You absolutely have to use linear activation for regression tasks because you need the output to be a continuous numerical value, not bound by limits like 0 or 1.
Right. So let's discuss the training configuration. What choices did they make about hyperparameters, and what was the goal of the loss function?
They use the atom optimizer, which is a very popular and robust choice for training deep networks. The loss function was mean squared error, or MSE.
And why MSE over, say, mean absolute error, MAE, for training?
Well, MSE penalizes larger errors much more severely than MAE does. In the context of adaptive optics, getting a coefficient significantly wrong can catastrophically degrade the beam.
So you want the model to be terrified of being very wrong.
Exactly. You want the model to avoid large prediction errors at all costs to ensure the predicted phase map is at least in the right ballpark. MSE enforces that strong aversion to large deviations.
And the training itself.
The training ran for 10 epochs with a batch size of 32. The dataset was split 70% for training, 15% for validation, and 15% for testing. And given that tiny dataset, they couldn't really afford explicit regularization like dropout, so they had to rely on the inherent regularization provided by the small dataset and the constrained architecture.
So the ultimate question, could this compact network, trained on a meager 506 images, actually generalize and provide accurate physical predictions? This is where the engineering feasibility is really determined.
The training curve showed rapid initial improvement, which is typical. By the 10th epoch, the accuracy on the training set reached a pretty impressive 92.33%. The network had clearly mastered the data it had seen.
But, as always, the true measure of a model is how it handles brand new information. What was the performance on that unseen test set?
And this is the key result. The final evaluation on the test data achieved 80.39% accuracy, and this is a really significant outcome, especially given the tiny size of the dataset.
It is, but that difference between the 92% training accuracy and the 80% test accuracy, that clearly confirms the presence of overfitting.
Oh, absolutely. That was predicted because of the data bottleneck. The model is definitely learning some noise specific to the training set, but its ability to generalize, even at 80%, is still highly promising.
Let's provide some context for that 80% accuracy using the mean absolute error, the MAE, because that's the true measure of how close the predicted coefficients actually were.
Right. The mean absolute error on the test set was 0.1208. To frame this in practical terms, the aberration coefficient spanned a total normalized range of about 1.2 units from, say, negative error 0.6 to positive 0.6.
Okay.
An MAE of 0.12 means the average error in prediction is roughly 10% of that total dynamic range.
So on average, the prediction is off by about 10% of the maximum possible aberration. Why is that 10% error considered acceptable or even successful?
It's all about the speed trade-off. Manual optimization takes hours or days. Bayesian optimization takes tens or hundreds of iterations. The CNN provides a correction prediction instantly from a single image.
So it's a massive head start.
It's a huge head start. That 10% remaining error is small enough that it only requires a brief, fast, local refinement step, maybe a tiny BO loop to lock onto the final optimal position. It converts a days-long problem into a minutes-long problem. Achieving 80% accuracy instantly is radically better than starting from zero.
So let's synthesize the two machine learning solutions. We have two Very different viability proofs here.
We do. Bayesian optimization provided structure, interpretability, and a guarantee of finding a local optimum by systematically exploring the space. It was the necessary analytical baseline.
But it was slow.
It was slow, it had a sequential bias, and a very limited objective function, focused only on peak intensity.
And the CNN.
The convolutional neural network demonstrated the potential for real-time capability. It captured the complex, nonlinear coupling between aberration modes by looking at the beam shape itself. Its 80% accuracy confirms deep learning's power to skip complex phase reconstruction and move straight to diagnosis and correction.
So the conclusion has to be that machine learning provides the viability for automated aberration correction, but the two methods offer solutions to different operational problems. BO for deep offline systematic search, and the CNN for fast real-time feedback.
That's a perfect summary. The major limitation, though, remains the one we discussed, that small dataset size of 506 images. If they could expand this to 5,000 or even 10,000 images, that 12% generalization gap between training and testing would almost certainly shrink dramatically.
You could push the test accuracy up towards 95% or higher.
You could.
So what does the roadmap look like for pushing this technology from a proof of concept to a standard operational tool?
Well, they listed several critical future directions. First, they need to expand the scope beyond just Zernike orders 4, 5, and 6, including higher-order aberrations like trefoil and secondary spherical aberration would provide a more complete and realistic correction for a real-world system.
And then the really exciting step.
The most exciting step is implementing the predicted coefficients into a closed-loop correction system. Right now, the CNN predicts, and a human evaluates. In a closed loop, the prediction is immediately fed to the SLM, the resulting corrected beam is imaged again, and the CNN provides a new, refined prediction in milliseconds.
That's true adaptive optics.
That is the definition of true adaptive optics, and that closed-loop system is essential for overcoming that 10% MAE. The CNN gets you 80% of the way there instantly, and the closed loop handles the final 20% cleanup.
What else is on the horizon?
They also plan to investigate transfer learning. Since generating 18,000 real images in a lab is incredibly costly, they could train a foundational model using thousands of simulated images, where the true aberrations are perfectly known, and then fine-tune that model with their smaller set of real, messy experimental data.
That bridges the data gap efficiently.
It does. And beyond that, they have to explore multi-objective optimization. A hybrid system could train the CNN to output not just the coefficients, but also a predicted Strail ratio. The optimization loop could then maximize both peak intensity and beam quality simultaneously.
And finally, the hybrid approach. It seems logical that the ultimate system would be neither purely BO nor purely CNN.
Indeed. The ideal system would leverage the CNN speed for an instantaneous first-pass correction, getting this system 80% of the way there, and then employ a quick, targeted BO search loop that operates only on that final, small remaining error space.
You combine the systematic robustness of BO with the real-time speed of deep learning.
And you potentially eliminate manual alignment forever.
So what does this all mean for the future of ultra-fast science?
Well, it means the operational headache that has plagued these advanced laser systems is nearing an end. Bayesian optimization proved that we can systematically search for an optimum, but the convolutional neural network showed the path to real speed.
It demonstrated that a machine can look at the pattern of light and instantly understand the underlying physical distortion. It can diagnose complex problems faster than any human expert could ever dream of.
And that ability is transformative. Stability and consistency are the enemies of high harmonic generation systems. If you can use that 80% accurate CNN prediction to set the phase map and then follow it with a quick automatic refinement loop, you eliminate system drift as a major experimental variable.
The system just maintains optimal performance automatically.
Exactly. It makes high harmonic generation sources reliable enough for routine, complex research applications outside of the few highly specialized labs that currently dominate the field.
The ultimate provocative thought here builds on that vision of automation. If machine learning can perfectly predict the necessary corrective phase map for a laser system operating at 10 to the 14 watts per centimeter squared, what other physical parameters are out there? Magnetic field shapes, vacuum pressure optima, temperature stability points. What else is waiting to be automatically diagnosed and corrected by a neural network, just looking at a simple visual input? This work isn't just about flattening a beam. It's a blueprint for automated physics discovery itself.
A profound thought to end on. Thanks for diving deep with us.